A very warm welcome to all of you. Good morning, all. Once again, I welcome you for this webinar on deep dive into SOLIDWORKS Simulation Standard. So I'm Manu. I'm taking care of all the simulation activities at Beacon and working as a senior application engineer. And let us begin this webinar. So basically, to begin with, majority of questions arises why we require simulation. So as you are aware, we are into a new era where you can say that from the old age, how we have evolved ourselves, our products, right from the crude stage to now advanced prototypes or the products there. So basically, the main thing is we want to have a better design at a reduced cost and shorter design cycle. So that is the main intention, and to avoid any of the failures which might occur during this phase change from the old product designs to now latest product designs. So that is what we go for, looking for the simulation, and we want to also avoid the number of prototypes which we do testing in our real-time scenarios. So question arises again, what is this simulation? Simulation, as you most of you might be aware, but still I want to repeat here, any numerical technique which you use to predict the behavior of the systems, assemblies or components is known as simulation, and it is an approximation where we can, instead of going for real-time testing, we can test them inside your system itself. So we have a different approaches. Finite element method is there, boundary element method. What you are observing here, this is a finite element method, and this is a control finite volume method also will be there for flow analysis. And you can also have the boundary element method, which are the different analysis which you can use it to check your system's behavior, how they are going to work out in a real-time scenario. So just want to inform you, like SolidWorks is a SolidWorks simulation comes with various simulation tools available, and when it comes to FE tools, what you are getting SolidWorks simulation we call it, and when you go for the CFD or finite volume method, so in that cases we call it as a SolidWorks flow simulation. So that will help you to understand the flow of the fluids. It may be of internal, external, or it can be of mixed also. You can consider those type of analysis in flow simulation. In when it comes to your plastic components, we have the SolidWorks plastics available, so which will help you to understand the defects which are occurring inside your product at the beginning stage itself. And if you want to check out like how the behavior of your components or the kinematic mechanisms will work, we have a solution called SolidWorks motion analysis that is completely dedicated to check for the kinematics of your products. So we have a different solution, as I mentioned in the simulation structural analysis itself. We have a simulation standard, simulation professional, and simulation premium one. So today we are going to focus on these set of solutions which are available in the simulation standard. We have much more capabilities where we can perform the frequency analysis, buckling analysis, thermal, as well as dynamics and nonlinear analysis in our professional and premium set of bundles. So this is a set of solutions which will be related to the flow simulation, what we call as a CFD analysis, where you can perform internal, external flow analysis, thermal analysis. You can easily perform. You can also check for the comfort parameters or advanced radiation, which comes in HVAC. Or many of your industries are now becoming a mechatronic also. So we want to see that one, how the heat and the mechanical systems generated by them, as well as the electronic components which are allocated on them. So you want to see that one, how the heat dissipation occurs. So those type of analysis also we can check out inside. We have a built-in library for this where we can perform the flow analysis also. And if you are dealing with your products which involve plastic components, so those components, you want to see that when any defects are occurring, or in the you have a certain type of like criteria where you have to check for the shrinkage, and you want to see that one how the warpage will happen, or you want to go for some runner balancing, those type of things. Complete solutions for injection molding requirements can be also achieved in simulation. Now, question, many of us we might think like, okay, why we have to go for SolidWorks simulation? Why it is much more better to go for that one? So, as a SolidWorks user, I have already whenever I design a product, I always think like, okay, this my product will work fine or not. So for that, I have to rely on the testing facilities, or I have to rely on the analyst who is going to perform. So I have to just build it, and he will perform the analysis for you, and he has to tell that, okay, this design is not working, you have to make change. So this can be completely eliminated when you work on SolidWorks simulation, where the native geometry you can take out just in a tab. What you are observing here in this slide, in the just tab, you will also find a sort of simulation module is also available, which a designer can also use the same thing, and he can perform, and he can only understand where he can have to make the changes. So it is very easy to learn, a very effective one, because as a designer, I know my products, how I have designed, and what basis I have changed the parameters or designed the parameters. So it will be much more easy for me to judge and make the designs much more easier, and the cycle which is taken like for all these changes there, so that I can reduce completely when you use CAD integrated simulation, what we have in SolidWorks simulation. And one more benefits what you also observe here, we will get a complete support from our technical team also, and in every releases, the each parameters, for example, suppose many of things changes in the latest technology we might be changing, or the requirements might also get changed. So these requirements also taken care by SolidWorks development team. So every year they will include those things. So it will be like enhanced technology which is given to a designer level also, who can utilize and bring faster the designs with whatever the best possible he can give it to the market, and it saves the cost. That's one of things. So whenever come to the linear static analysis, today we are going to deal with most of them as a linear static analysis. So in this webinar, so where we are going to see that one, when we apply a load on the applied fixtures and boundary conditions, how the product or that part or an assembly will going to vary. So how it's going to react, that we're going to find out. Usually we use this linear static analysis to find out the strength of our products, and we compare them with the yield strength of materials to understand whether it's going to have a failure or not. To begin with, like finite element analysis, what you see here, so the person who is very new to this term, you can see that finite element analysis, you will consider it as a rope is there. What you are seeing here, it's rope. Suppose I want to measure that length of that rope with a small scale, what is mentioned here. So I have to break down into small elements here like this. What you are seeing here, this is a scale. I had to put the scale like this, and I have to measure the complete length of that rope. So this is a similar way how finite element analysis will also work. We are going to break the complete model into small elements which are interconnected by nodes, and we are going to calculate the stresses, strains, and displacement on those elements. And what are the assumptions we do in linear static analysis is you can see that we assume that the loads are varying, loads are not varying with respect to time, they are going constant, and they are applied slowly. So that they're not, there should not be any impact type of flow. And we also assume that when suppose we apply a load and we're getting a stresses, if it is a F there, if you increase the load by twice, so the displacement stresses also will will double. So that's how we are going to consider. And material will consider as a linear material, and there are no permanent deformations occurring. So any analysis, whenever you want to prepare, you should make sure that the complete CAD model is available with you. You can make some changes in that model, and it is up to you that one which portion of that model is very important. So you have to perform the geometrical simplifications when you want to perform the analysis. So let us see here how it goes from the CAD model to complete end of the stress results. So if you take out this is a bracket is a CAD model. So if I'm applying the load on this top of this face, so I can remove the some of the fillets which might not require. So that is a simplification of your model. It is a must whenever you are going to perform the analysis. So those results, then this model is taken inside the simulation module, where we are going to define which type of analysis we want to perform, what are the material properties, where it is supported, where it is load is applied, where completely this defines in the 5 steps. So after this one, we are going to make it as a discretization. So usually, as you might be aware, the FEA analysis will happen in 3 stages: pre-processing, processing, and post-processing. So whatever we till now what we are doing up to the discretization, where the splitting of the model into small elements, it is called as FE. It is called as pre-processing in FEA. Now after this one, we will be having the solver. Using the formulas, it's going to calculate the stresses acting, the displacements, as well as the strain in your model. So you can see the results in this form of FEA results as a plots, which you can identify with we can identify where the stresses are maximum, where the displacement is maximum, and strain is maximum. So let us consider we want to analyze one of the part of complete this vehicle. So this is a vehicle is available. Instead of this one, say I have to reduce it, I can suppress or I can take out a sub assembly of this part, and I can just go for selection of whichever part is required or assembly is required. So that is how you have to simplify your model. Unless until it is required, you need not take into account the complete assembly. Suppose here I want to just and analyze this bracket only, I need not consider complete assembly for that. I need to just go for simplifying the model. You can see that one from complete vehicle assembly, I have taken to this range. So I can consider only this part. This bracket is very much important for me, where we are going to go for the wheel alignment, and you can go for other things also there. So that you can easily identify. So boundary conditions play very important role. You need not consider the complete assembly. You can consider a system level or component level also. So that will be a better control on your products whenever you are going to analyze your products. So different types of boundary conditions when you are dealing also, it may be of cantilever beam, what you are seeing here, where all the translations and rotations are fixed. So these type of consideration also we have to consider. A guide support, what you have seen here in the previous one, where only translations is there. So as realistic, you have to model that and you have to define the boundary conditions. You are seeing here spline joint, what you are adding here, only axial translation is allowed. A pin joint, what you're seeing here, only one rotation is allowed. So accordingly, understand your complete mechanism or how the parts interact with each other. It can be a ball socket one or roller support. What are the degrees of freedom? How much degrees of freedom it will be there? So that you have to understand and assign those things to the different parts as much as possible. So various types of boundary conditions you can apply here. If you see that one, I can apply any of a fixed condition here. It can be applied on the face level, it may be applied on point, or it may be on the edge level also. So you can easily apply the fixtures, which will help you to correlate with the real-time scenarios. Different types of loads also you can apply, where you can see that on the forces you can apply, pressures you can apply. So usually forces, what you're seeing here, those will come in this in pink or red color, and what you're seeing in green color, so those will be the fixtures. Coming to the mesh, so mesh is a you can see that one, it is an approximation of the CAD model when you are performing the analysis. So usually this modeling, this analysis will depend upon the material properties and meshing. So results of your the results of your analysis will it will be dependent mainly on these two, most of the things. So if you are able to capture the mesh properly of your part or at an assembly, then the results will be much more accurate, and you can expect the same type of results in experiments also when you are going to perform. And the elements interact with different elements through the nodes, what you're seeing. So the load will transfer from one element to another element in the form through these nodes only. So as you're seeing, you might have seen this type of here, where you can see Lego toy will be there. So these you can consider it as a elements, how they are connected to each other through the nodes. So that is how you can imagine if you are new to this finite element analysis. Then different types of elements what we have in SolidWorks simulation. We have tetrahedral elements, which is of you can say 4 noded, or it can be of 10 noded. Here we can have any of the solid parts, you can consider them for meshing itself. So it is very easy to perform the meshing of that one. If you are having a shell element, if you are having a sheet metal components, you can also have a lower order elements, higher order elements of trias are available, which you can use it. This is a lower order element, what you're seeing 3 noded. So you can easily take the geometry, and you can capture the shape also. And for the structural elements, we can also have beam elements. 200 beam elements are available, so that will help you to completely capture the structures, the shape and size. One more question arises whenever whether you have to go for higher order elements or lower. What you're seeing here, no, these are the lower order elements, and what you're seeing here, this is the higher order elements. So we find the mid nodes in the higher order elements, that will help you to capture the shape of your products or of your models as much as possible. So if you consider, okay, whether have to go for the higher order elements or lower order elements. So one example, if you take out the same cantilever beam, and if you are applying a load at vertically downwards on one of the ends, so you can find out that there will be differences in your results also. So as an analyst, you should be also capable of understanding how results will going to vary, and which elements you have to use it also. So if you consider higher order elements, whenever you have you can say bending is dominating in case of your analysis, then it is better to use the higher order elements. In case of axial and shear dominating loads, you can go for the lower order elements, which are economical in the sense the competition time will be less. So that also you can consider it here. Then question arises how actually finite element analysis will work. So usually based upon the formula F equal to K, you might be knowing this one. This is again the force will be calculated by displacement and the spin K constant. So first, usually what will happen, we are going to calculate the displacements of the each elements, which will form as a matrix, and that will be that from that we are going to calculate the displacement. Sorry, force will be available with you. Then K will also be available with you. You are going to calculate the displacement here. Then after that one, that displacement, we are going to use it to calculate the strains. Then finally, we are going to calculate the stresses. So stresses are the final outcome when you perform the analysis. You might be using it first for the for judging out the failure, but that will be the last is going to calculate it from the displacement, then strain, then by Young's modulus we are going to calculate the stress results. So in majority of cases, whenever you go for any of the analysis, we use the one message stresses, which we are using for comparison of our results, and we are going to compare these results with the yield strength of our components for getting the you can say factor of safety, or how we are going to fail. You can compare with the engineering stress or design stress also. So why one versus is considered is because it is an equivalent stress, where you can see it will consider all the normal stresses, shear stresses, and it is also possible to include the principal stresses if you want, for comparison of your results, whether you are seeing that your product are failure or not. In case of assembly level, when we have a different yield strength materials will be available, we can also use the factor of safety plot, which will help you to calculate maintain the factor of safety of each components, which might be like for 1.2, 1.3, or it may be 4, 5, as per the criticality of that component, how the working of the component will happen. In case of post-processing, what you are observing here, so a lot of options you are going to get it. You can get a stress plot, displacement plot, strain plot. You will also see that design insight also will be available, which will help you to identify where the loading will be more and where the stresses are more, so that you can make design changes in your model. So let us take one example. I hope everyone is able to see my screen. Yes, sir. Yeah. This is a simple cycle frame I have taken here. You can take out for any of your assemblies model here. So what are the benefits I was telling about? The same model I can take out just by adding this SOLIDWORKS simulation. I will get an options here where I can go for creating a new study. So in the new study, depending upon your license, you are going to get it different study capabilities here. Presently, we are going to just have an option here in the simulation standard. We are going to get static analysis, and we are going to see the fatigue analysis here. So this is an assembly, and one of the benefit of working with SolidWorks is you can take out the same method or what you are using for the materials which are used for in the part level or assembly level itself. So when you go to the material applications, so you are going to get all the materials which are already available, most of them which are available, which are used in the market. So usually it will happen in 5 steps. One is you are creating the model, so that's a geometric population. Then you have to create you have to define which type of study you are going to go for adding. So suppose I want to create I want to perform a static analysis, I have to go for static analysis. Then we need to apply the materials. So depending upon your requirement, you can apply any of the materials which is going to be required. And one more good thing about SolidWorks simulation itself, at the beginning level itself, it is going to showcase you which are the properties are mandatorily required for performing such analysis. There will be a color coding. What you are seeing here, the red color indicates that that property is mandatory for performing this type of analysis. If I go for any other analysis, so these colors or different properties will change. You can see that one, some color properties are red color. These are important one, required, mandatory one. Blue color, if you are having, you can add them, so that will also be included in the analysis. The black color, what you're seeing here, that indicates it's not required in this analysis. Okay, and once you add the material, then you are going to define the connections. In case of assembly, I want to define how they are these components are going to interact with each other. You can see that one, these are the different bodies or parts are available which are connected by weld connections here. So you can also take into help what type of weld do you want to add, so how they are going to interact also. So these surfaces will be having weld connections here. This is a edge weld connections which is added, which is going to bind this part, this body with this body. So similarly, all the parts are binded here by the welds as you're observing here. Can see that one everywhere. I can just observe here. Once you click also, it is going to showcase you the parts which you are going to use for adding the weld connectors. And one more thing, so this is interaction, how the components will interact with each other is added. Once you add that interactions, we'll go for the fixtures where it's going to fix. So you can just go for here. I want to fix this at this position. Okay, this is a cycle frame, what you're seeing here, or bike frame. So we are going to fix it at this position. So we are going to add a fixture there. So you can neatly understand, okay, where the fixtures is added. So different types of fixtures you can add here, roller support, hinge connections, any of the bearing also you want to go for adding. So different types of advanced fixtures are also available. So that will help you to constrain the degrees of freedom so that it will be much more realistic to your experimental tests also. And after adding the fixtures, I need to just define the boundary condition, the loads here. So this is the boundary condition what I defined. I want to apply a load. For example, here I want to just apply a load at this position. It is as good as, for example, I'm hitting my front wheel of a bike, or the back wheel of the bike. I'm going to hit it in the some of the, say, humps are there, or some it is on the road also. So what will be the stresses developed due to that one on my frame? I want to find out, so I can take out help of any of a direction here. I can just define the loads which I want to define. So this is easy for us to say understand where I applied the load, in which direction it is applied load. So it's very easy for any of a designer also who is new to this simulation. He can easily understand. Once you've done that one, you need to just run this. So you can see that within a few clicks, or say few steps, I am able to apply the material. I'm able to apply the connections, how the components are going to interact. I'm able to apply the boundary conditions, which will help you to take out the results accordingly. So I can just say, after running that one, I need to just run it, and I can understand how the behavior of the components will happen. You can just observe that one. So this part, or this welds, it might happen have much more stresses. So it is very easy for us to understand by this color plot what you're observing on the right side. Red color indicates it's maximum stresses induced, and blue color indicates it's very less stresses induced in that one. And by seeing this also, if you can compare to the my yield strength of this complete bike which I am used, so that I can compare with the results. You can see that one, it has crossed the 37.53. So it might fail in this region. So I can easily understand by this type of analysis. So quickly I can able to add the boundary conditions, and we can find out the results from this analysis. You can compare the various results also here. If suppose I want to just compare the results. So I have calculated the factor of safety also. You can just observe here, the factor of safety plot also will showcase you where the factor of safety is less than 2. You can easily use these type of images or animations which you can add it in your report while showcasing with the client, or you want to make some design changes also. So this will help you a lot. Again, I'll switch back to the PPT. So you have seen that one, how we can go for applying the boundary conditions. We can apply the meshing also. And one more tip for you, it's not like always you have to take out a complete assembly. I can simplify this model as much as possible. What you're seeing here, this assembly, I can make it as a single part like this, or I can simplify it like this also. Suppose these are 3 different parts are there, I can able to make the changes like that, so that it will be easier for me to run the analysis and get the results much more faster. So I already have showed you like how to apply the materials, and one more thing, you can add your custom material also. Like many of cases, we might require custom materials, and we performing the annealing, or we are making some changes in that composition also. So it will affect their strengths and the properties. So that also we can create custom properties, and we can apply to the required parts or assemblies. You have seen that one different types of boundary conditions we have applied here, how we applied, and it will help you to get the similar test conditions what you applied for the main parts also. So various load types of loadings also I have just added for your reference here. Not only the forces, it can apply torque, pressure, gravity, even centrifugal forces you can apply, bearing load you can apply, temperature loading also sometimes it's very much important nowadays, because it might lead to crossing of the yield strength. Suppose your factor of shift is very near to the one, so in that cases little bit heat also it might change your component properties and it might fail. So all these loads can be included in your analysis, and you can perform the analysis. And this is the advanced reference geometry what we have. So this will help you to restrict the degrees of freedom of like what I have mentioned, showed in the earlier one. So you can restrict the movement along x direction, y direction, the translations as well as the rotations. You can take help of the faces, edges, planes, or axes for defining them. So meshing, as I said, we have three types of meshing available there. We have the standard mesh, we have a curvature-based mesh, and a blended curvature-based mesh. So this will help you to completely capture the shape of your components. So those are broadly divided into two types: what is compatible and incompatible one. That meshing. So compatible meshing, in the sense you can see that one, there is a complete improvement of this component. This is a rotor blades. So same type of elements will be added on the connecting component, so that the transfer of the load, suppose you are applying a force on these blades, so that gets transferred to the rotor also. So this will happen as a compatible type of mesh. In case of incompatible one, what you are observing here, there will not be exact node to node connection. The node to elements connection will going to happen, and this is also one way of performing the analysis whenever you have a very large components and small components are there, and it was not possible to add a complete compatible mesh. In that cases, this flexibility gives a designer to add incompatible mesh and perform the analysis. You can just observe here the comparison of different types of the meshes which are available inside the SOLIDWORKS simulation. You can see this is a compatible mesh, this is a standard mesh, and we have the curvature based mesh. So this method, it automatically adds more number of elements in the curvature areas, and when compared to the standard mesh, which will maintain the same element sizes. You can see here, no, the number of elements will be more in curvature when compared to the other portions. So this is also the SOLIDWORKS simulation is intelligent enough to identify where the it should add more number of elements to get a proper results. So I already have explained you, like we have three different types of meshing. So this is a solid mesh, shell mesh, and you can see that one, if it's a sheet metal component is there, automatically we are going to have a shell mesh here, and for the structure members, if you're carried out in the weldments, so it will be created in the form of beams. Now coming to the one more concept, what we are getting in the SOLIDWORKS simulation standard is a trend tracker concept. You can see that one many times whenever you perform the analysis, there are the design changes will occur from say version 1 to version 10. Might be, it might happen, or it might be version 1.A, 1.B, 1.C. Means there are small changes in their versions also, or some revisions will occur. So in that cases, let us see here, this is a connecting rod. I want to see that one, which will be my best design for that one. Here, the test conditions will be like, I'm going to have a bearing load at this condition. Here, it is having a hinge connection, and in this portion, there's a fixture connection is available. So I want to see that one, how that component will going to behave. I'll just play you a small video I created for that one. So when you go to SOLIDWORKS environment, I will just go for a new study. I'll tell you the procedure what I'm going to perform here. I'm just going to apply the fixtures, whatever I defined, like I have applying, going to apply the hinge connections at this location. Then I'm going to perform add the fixtures. It's going to fix up with the help of bolts or connections here. I've added a fixture in this portion, and here I'm going to apply the bearing load, the forces I want to go for applying, and I can take help of different types of planes also to define the direction, in which direction I want to apply. So here I'm entering the load of say 2220 Newton of load in the vertical downward direction. So once you apply load, I need to just run it. Automatic meshing of your component will happen. You are going to see some results of this one. So I can see my factor of safety plot here, where the factor of safety, the FOS is minimum. I want to see the minimum value, so that is coming around say 8.936. So this is a minimum factor of safety. So this shows that I can reduce some of the mass. So for that I will take help of the trend tracker. So I'll just add a trend tracker and set this as a baseline. So this is my reference. I'm going to vary I check for that mass, how it's going to vary also. You can see that these are the plots which I'm going to obtain from the trend tracker itself, which is the mass, stress, and displacements. It will also add a sensors here, what you're observing, mass, stress, and displacement sensors. And now I'm going to just go for adding out one more sensor or the factor of safety I want to just check out. I'll go for adding that factor of safety also. So different types of sensors, you can just select it, you can add it here. I can want to see the stress intensity also, you can just go for adding that one also. Now I can just go for add different types of graphs also, which I want to note it for each iteration I'm going to perform. So I'll get a complete graph of performing the analysis there. So I want to make some design changes. I will try to make some changes in the thickness of this connecting rod. Now I will just rerun it. Okay, I'm not going to do any changes other than that one. I'll say okay, add it to my trend tracker. So automatically, if you see my results, now the factor of safety is 7.8. It has reduced from that earlier value, and this result is also noted in the form of graph. And mass also it's reduced. Stress has increased because definitely thickness has reduced, so stress is increased. Now again I will go for some design changes. Here I will try to add one extrude cut. I will try to remove the material. Let us see that one, how it's going to behave. So through all cut I'm going to add, and I'm going to see that one, how my results get affected by this connecting rod. So I'll just rerun it. Again, see that one trend tracker will note down my results, and it is going to plot that one also. Now you can see that one, it has reduced from 7 to 4. So as per my requirement, you can see that one, the mass is getting reduced. I can reduce the mass as much as possible, and it should not go to failure range. So that is also I had to take into consideration while selecting the best design also. I'll make some little bit change. It is little bit for I want to just add some material here, and let us see that one, how my results will get changed also. Earlier I removed material. Now using the same sketch, I will just add thickness for this connecting rod, and I want to check out how the results will going to vary. So this is again, I'll go for the mirror option. I'm going to mid plane option. I'm going to use it, and I will add a thickness of required 4 millimeter. So it will added a material now. Earlier I have removed a material. Now I added a material, a small amount. Let us see that one, how my results gets affected by this change. You can see that one, I have performed the 3 analysis, and from this I want to note down, okay, what is my result. See here now, I have reduced the mass, but the factor of safety I have kept it at 7 itself. So that is one of the things. You can see that stresses also is much more lower when compared to that cut extrude what I have done. You can also take out the images of that one, which you can use it for the presentation purposes. Automatically it will create a gallery of those images of all these plots we can easily understand. It is also possible to switch between the different iterations also, from baseline to iteration 1 to iteration 2. So this is one way of doing so you can say optimization of your products also, and finding out the best design in that one. So what you have seen now, we have want to verify the design strength of this connecting rod. So trend tracker, we have used it now. We have set the baselines, and we have made multiple design changes. And how you note down? We note it down using the sensors. So this is how the SolidWorks trend tracker will work, and all these sensors will help you to note down each of the results in the form of stresses, displacement, as well as the mass also. So one by one, I'm going to go for selecting all that. So you can see that one, these are the different design changes what we have done. What we have done from this one, I can get to know that one. Okay, I can decide which is my best design. So from this, I can easily understand what is my best design of that one. I can see that one, okay, the third option, it seems better. When you consider here, which is A, B, C, the changes what you have done. So third design is the best because I have removed the material also, and I have maintained the factor of safety near to that earlier value only without affecting that one. Okay. So that is how the trend tracker analysis will help you for selecting the best designs in your model and reducing the mass as much as possible. Now, one more analysis what we look for is the fatigue analysis. So fatigue analysis, in the sense, whenever you perform the analysis on any of the parts or assemblies there, we apply only once the load, and we see that one, it might fail or it might not fail. In that cases, we want to understand, okay, whether how much duration it's going to be available without any failure. In that cases, fatigue analysis will be very much important. Sometimes you can see that it will take out years of time to see also, because as a manufacturer, we are going to give a warranty of say 1 year, 6 months, 3 months. So how we'll get to know that one? So using this fatigue analysis. So usually this fatigue analysis is dependent upon SN curve. So what you are going to see here, how the stresses will vary with respect to the number of cycles. So that is what is required, the fatigue curve data, which we can feed it inside the SolidWorks simulation, and you can get the results. So you are seeing here, this is a stress ratio what you are seeing. So this is a number of cycles what you are seeing, and this is the stress values what you are getting from the analysis or the test setup. Once you have to do that one, you can import data inside our SolidWorks simulation, and you can perform. So perform the fatigue analysis. Usually fatigue analysis can be of constant amplitude, or it can be of variable amplitude. What you're seeing here, no? It can be a constant or variable, and also it is possible to have say different types of analysis when you perform the fatigue. It may be of harmonic also, loading can be there, or it may be of random type. So all these you can include, and it is very easy where you can mention that how what is the total number of cycles you want to test the analysis. I'll just show you one example on this crankshaft. So how which design is better when you consider the fatigue analysis. So different materials, fixtures, loads, we are going to solve it here. So first we are going to use the materials which is already available. You can include the custom materials also. So it will be same existing the fixtures what you're seeing here. These are the hinge fixtures we are going to apply on this crankshaft, and we are going to apply a load as good as I'm going to put my foot on that paddle there. I want to see that one, how many times or how many number of cycles it can withstand without any failure. Some of people, you might have seen that on in cycles also, they will stand on that one and they will going to paddle it. So what is the effect of that also you can understand. So you can include the loads on that paddle, and you are going to solve that analysis. So let us switch back. I'll just show you how the fatigue analysis will be carried out. Okay. This is a simple analysis. So before the fatigue analysis, always you have to perform a static analysis. So that will be the the uh, input for performing the fatigue analysis. You are seeing here. This is the crank assembly. What you are having. There are different designs you can create here inside the configuration also, which you can use it as per your requirement. You can see different designs, so you can add out. So this is one of the benefit of using the SolidWorks simulation, where I can just go for switching from one configuration to another configuration, and I can identify, understand that how they are going to behave inside my SolidWorks simulation itself. Okay, let me activate this. I already explained you what are the boundary conditions I have applied here. I'll just show those once again here. You can see here, these are the fixtures I have applied, and I have applied forces here on this force. Suppose I'll go for showing the results after run. So how it is going to behave? You can see that when you compare to the yield strength of this complete assembly, if you consider it as a single part, so you can see it is very less. So it is 214 is the stresses which are developed inside the when you're performing the static analysis. It shows that it is not failing right now. So in that cases, if I go for saying that okay, this component has passed. So suppose he work, some of people will go for taking it for a month, where he crosses 10,000 cycles. It might fail in that cases also. So for checking that one or giving the warranty, I need to just go to creating a new study. Here I'll get option to define the fatigue analysis, where I can have different options with constant load, variable amplitudes, with harmonic load or sinusoidal load. So you can easily add out. I will create a new fatigue study. In that one, I will just need to add an event here. I need to just go here and suppose I want to apply the material. So I will say no. Here we require SN curve, that is number of cycles, how the stresses are varying with these number of cycles. I need this data. This data I have fed it here, and I'm going to perform event here. So here in this event, I need to mention that one, whether the loads are fully reversible or it is just applying only you can go for. So I'm allowing you to retract back, so that is fully reverse what you're seeing here. So I can mention how many number of cycles is required for that analysis you can perform, and I can get the results also. So let us switch back. So this is, I have carried it for different designs also. Let me compare the results here in this PPT due to the time constraint. You can identify displacement, stress, and factor of safety. Once it is done, I will just go for the fatigue analysis. See, this is how actually you can see that one, how it is performed. You have to run that analysis. You can see here, I have to completely go on applying the load, and I have to test it in the experimental setup. So that will be very difficult task whenever you want to go for performing analysis. So you have to completely go on applying the load. So it might lead the failure after some time. So usually the fatigue analysis is very much required for each and every component. Every manufacturer has to perform this analysis. And one more thing I want to tell you, this fatigue analysis is available in the standard itself. It is one of the say high-end analysis. So usually you will not find it in a starting level of analysis, which is a linear static analysis in the SolidWorks simulation itself. It's a great tool, a great inclusion in SolidWorks simulation standard itself to perform the analysis. So you have seen that one, we have applied the different events here. This is the number of cycles, and I have taken the static study as a input for that one. So after running this this static study, it will be run for these number of cycles, and it will throw up results in the form of damage plot or life plot. What you're seeing here, so this is minimum number of cycle. This is the minimum of cycles it can withstand without any of the failure. You can have a damage plot of on, so that one it will give the percentage how it's going to where it is damaged. When you compare all the three here, you can see that one here, I'm getting, say, these are the number of cycles. Say I'm okay with this number of cycles. Suppose if it is fine for me, I can switch to, I can take out this design for my manufacturing or supplying it. So this is how we can check out different types of fatigue analysis after performing the linear static analysis. Okay, this is how the factor of safety variations will happen. I have just plotted in the form of table. You can see that one, okay, this factor of safety for this one is better, and it is very much high, say around 13.63 million cycles is the product life, and considering the factor of safety is also good. So I can consider the design to as per my requirement. So let us quickly move to the one more analysis, which is very much important whenever you perform any of your machine related or the mechanism related type of analysis. We call it as a time-based motion analysis. So here we are going to give in the form of we are doing input in the form of motors, and we are saying that one how the component will going to interact with each other, and we are going to find out what will the forces, what will be the how the contact pressure is acting inside the on the different components. Let us switch back to SolidWorks. So to begin with, just I want to show you a simple mechanism which you can use it for performing any of the tests for mechanism also. So this is a wall cam mechanism. What you are seeing here. See, I'll just play this animation. You'll understand what is happening here. The opening of the wall and the closing of the wall is happening in this mechanism. So how it is created, I just need to go for activating this SolidWorks motion analysis, and I need to just go for selecting here which type of analysis. I have to select it motion analysis. Here I have defined different contacts also. Here the cam and this plunger, the rocker, how they are going to interact, I have defined it here. So you can define the different types of contacts. You can also define the friction coefficient between them, how they are going to interact. So I have given it as a dry and greasy. You can have different types of contacts depending upon whether you are applying a grease there or how it works there. I have to define the contacts here. Here another contact is between these two components. I need to just define a motor. Here I have defined a motor, rotary motor. So here it will be connected to the motor. So this will drive this cam, and further rocker will also movement, and this will help you to open or close the wall. And I have given different speeds also here around 1200 RPM constantly. Different types of motion constant you can go for adding here, and on which phases is going to act like. So you can simulate and see that one how the interaction between the different components happening. So one more thing, I need to find out what will be the motor size to open and close this one. So that for that purpose also this motion analysis will helpful for you. And I have also defined a spring connector here. What you're seeing here, I have defined a spring between these two faces also. So the damping also have taken into account here. So different types of springs also we can define here. And suppose I want to see the plots where I want to just understand how the forces are reaction forces are acting. This is I want to see the contact forces between these two components. That's my requirement. So I need to just go for the plot here. I can define whichever forces. For example, here I want to define the forces. I want to define the contact forces. I want to have a magnitude between these two phases. So automatically that will be plotted in the form of graph. I'll just play it now. Just observe here. It will showcase the line you can see here. No, that indicates that one. The required reaction forces at different moment of time. You just observe here how the interaction happening, no, between these two phases, how the forces is varying. You can easily understand by this type of analysis. I want to show you one more example on this this motion analysis. This will be only one of the, you can say, useful things when you're performing the analysis also. So I want to see that one whether the mechanism is properly taking a path of this. And this is an assembly. I just defined it for motion path. So this is a path made whatever defined. I want to see that one how the component will move and what is the motor force is required for driving this to follow this path. So let us begin the same. Again, I'll go for the motion study. I need to just go for here. So I have to define. See, let us see here what I have done here. So I have defined a path mate. So this is a motor which is driven by the path mate. Whatever I have done here, I have just gone for the mate, and there is a path mate motor is available. You can have a linear motor, rotary motor. So here this is a path mate motor is applied, and I have defined that path mate motor to drive this complete assembly to follow this path. Okay, and let me just play this one so that we'll understand what I'm trying to simulate. You can see this is a complete analysis. What you're seeing, the mechanism is following that path completely, and it is going to add up. And you are also observing that one, the forces and speeds are varying with respect to the curvatures one. So what I have done here is I have used different types of segment motions also. Here you see here the segments are added. If I go for editing here, earlier I've used a constant one. I have given the start and end condition, and what will be the my displacement should happen. So for example, from 0 to 6 seconds, it will have 15 inches of displacement, and from 6 seconds to 1 second, I have given the displacement should be more. So I can define and control the speeds also here, the motor speed, you can define it also here. And suppose I want to plot out the results also. I want to see, earlier also I have showed you, I can plot the results. This plot is done to find out the acceleration, the displacements, what you're seeing here. This is find out the acceleration, and I want to find out linear acceleration on this face. So this is a component which is going to be connected with this path mate. I want to see that one, how it's going to behave. So let us see here, if I perform the analysis, how it's going to go for. So complete results will be plotted here. I'll just once again, I'll show you here itself. I'll just play. Just observe here how the movement of that assembly taking place on that path. So like this, you can create a mechanism, you can showcase during the concept design itself how it should work for, and you can use this motion analysis for designing of motors and interaction of different parts. You can also take these results in the SOLIDWORKS simulation. You get option here where you can take the results inside the SOLIDWORKS simulation FEA and perform the analysis whether they are going to fail with respect to that forces or loads or not. So various types of motors, springs, dampers, contact gravity, all these you can go for adding here, and all these settings I just clubbed out here. Springs you can define, torques you can define, contacts between how they are going to interact. So I've just put it in a single slide itself where you can see all these you can easily add out, and in the simulation standard we'll get a time-based motion analysis, which is also very much useful while predicting how the interaction of different components. As I said, these movements, these results, I can take it into FEA and I can perform the structural analysis. You can see that one, this is a door breaker, what you're seeing here. It's a spreader, how the movement of the spreader is happening here. So this is helpful for any jammed doors is there when accident happens there. We have to tear out that door and find out try to remove any casualties or any people are stuck in that one. So in that case it will help out. So we want to find out like how the movement of this spreader will happen, and I want to see that one any failure of this spreader arm will happen. So you can see that one, I can take it inside the FEA and I can find out the results of that also. Complete basics from the beginning itself, what is linear static analysis and what are the capabilities of SOLIDWORKS simulation standard, and when compared to the static analysis, it can be of trend tracker analysis, what I have showed, it can be of fatigue analysis, and the motion analysis which comes inside your SOLIDWORKS simulation standard itself. So this is very useful for a user to begin with and use effectively the capabilities to find out the failure of your products. So today we have just covered about the static analysis, trend tracker, fatigue analysis, time-based motion analysis. So there are a lot to cover in the SOLIDWORKS Simulation Professional and Premium capabilities. So this is one of the webinar on the first SOLIDWORKS Simulation Standard. We are going to do further webinars on Simulation Professional, where we're going to deep dive into those capabilities also, and we'll can see that it's an excellent tool, sort of simulation standard for using simulation. And as you know, for concurrent engineering, it will be very much helpful. Designer itself can perform the analysis, and he can only make some design changes. It will reduce the time of design changes, and also the cost incurred for performing also. And you can have a very good designs before manufacturing itself. You'll get to know that how they are going to behave. So thank you everyone for joining this webinar on the deep dive into SOLIDWORKS Simulation Standard.